The purpose of this video is to show you how to find the nth term equation of a quadratic sequence. And you may realize that this sequence right now is not quadratic, it's actually linear. And you can tell because 13 to 20 gives you plus 7, 20 to 27, and so on. So why am I showing you this example? Well, quadratic sequences are kind of weird, where you have to do two things at once. You have to do a quadratic part of the sequence, and then you have to find the linear part. So this is kind of a revision of how to find the linear part. Since the first difference is the same, you can say that this is a linear sequence or an arithmetic sequence. Okay, and the formula for the nth term of a linear sequence is un equals a plus n minus 1 times d. Okay, where a is the first term in the sequence, n stands for the term number that you're looking for, and d stands for the common difference. Okay, and we can simplify this. un equals 13 plus 7n minus 7. Okay, you really should know how to find the nth term of a linear sequence in order to do a quadratic. So if this is unfamiliar, maybe this review is not helping, then you should pause the video here, stop the video here, and go find a video that just is dedicated to finding nth term of a linear sequence. Okay, now that we have this out of the way, let's do a quadratic. This is going to be a quadratic sequence, okay? And I'll do this in blue. I'll do the linear in red and the quadratic in blue. Find the nth term of 15, 28, 45, 66, 91. The first step is the same exact thing as linear, so find the first difference. 15 to 28. Well, 15, 25, that's 10, plus 3 is 13. So that's adding 13. 28 to 45, let's see, 38 plus 7, so it's 10 plus 17. 45, 55, 65 is 20, plus 1 is 21. Just trying to figure out the first difference here. 20 plus 5 is 25. All right, so you can tell that the first difference is not constant. Okay, and that tells you that this is not linear. Not linear. Okay, and so the next thing you need to do then is check to see if it's quadratic. And it's quadratic if the second difference is constant. So let's have a look here. 13 to 17, you add 4. 17 to 21, aha. And then 21 to 25. Yeah, so it's the same, right? If your second difference is constant, then you have a quadratic. Okay, it's a quadratic sequence. All right, and so it's of the form un equals ax squared, and I'm going to start color coding. If you're a student of mine, you know how much I like to color code already. All right, so it's of this form where you have a squared part and a coefficient. You have a linear part, okay, and the constant term will be part of the linear part. What I'd like you to know is I guess that's kind of why I was using the word linear so much earlier instead of arithmetic, because I had it in my head that I wanted to have you guys realize that this is a linear answer, and this part of the equation here is also linear. And so what's going to happen going forward here is we're going to break this problem up, and we're going to find the quadratic part separate from the linear part, and then combine them at the end. It's almost as if, let me give you an illustration here. Okay, so let me just give a side example. Let's say I have the number 15, and I find one of the, if I take 11 away from that 15, how much is left? Oh, I can even color code it. I take 11 away from that 15, how much is left? Well, 15 minus 11 is 4, right? So you can see we're going to have our original sequence, and we're going to have we're going to have a quadratic part that we take away from the original sequence, and then we find a linear representation of that remainder. So I think it may be easier or it may be more clear as I go through here with this. Okay, the first trick is to find out what the value of A is. And it's always what the second difference is divided by 2. It's a little cluttered there, but you take that second difference and you divide it by 2, and that's what A is. So right off the bat, we know that the quadratic formula, the sequence starts with a 2x squared. I don't know what the rest is, and again, that's linear, but I do know that it starts with 2x squared. Okay, and it could just be 2x squared. It's probably not, though. Okay, well, if it was 2x squared, what would I have? If it was 2x squared, then I would substitute a 1 to find out the first term in the sequence, right? Now let's think about that. The first term in this sequence is a 15, the second term is a 28, third is a 45, fourth is a 66, and fifth is 91, right? And so if I wanted to do the same thing, down here, okay, find the term numbers. The first term in this sequence, well, oh, I used an X. I used an X here. I told myself not to do that, and I did. I'd like to make that correction. This is an N, and that's an N. When you're talking about quadratics, it's easy to use an X because it's very common. But when you're talking about quadratic sequences, it's all about the N. Okay, so I made that correction there. So back to this though. If I want to find, let's just pretend like this was our answer and I could circle it. It's not, but let's pretend. If it was, then if I plug a 1 in here, I should get a 15, right? So doing that, 1 squared is 1, 1 times 2 is 2. Definitely not 15, but I'm going to keep on going here. 2 squared is 4, 4 times 2 is 8. 3 squared is 9, 9 times 2 is 18. 4 squared is 16, 16 times 2 is 32. 5 squared is 25, 25 times 2 is 50. Okay, so you can see the sequence here is off. The original was 15, I can only take 2 away from that. The original is 28, I'm only at 8, right? 45 and 18. And so I invite you to think about that example that I gave earlier. For us, it wasn't an 11 that we had from that. I'm going to cross that off. The original number was 15. I took away a 2 from that because that's my first term in the sequence. So my quadratic part of this equation is taking away a chunk of 2 on that first term. It'll take away a chunk of 8 on the second term. And so I need to subtract away 2 from 15 to figure out how much I have left for the linear part. And I have to do the same thing for all the others. So 15, take away 2, well, that will make 13. 28, take away 8, can barely fit it, I think. 28, and take away 8 will make 20. 45, take away 18, well, let's see, that'd be 25 plus 2 is 27. 66, take away 32, 66, take away 30 would be 36. Take away 2 more is 34. 91 take away 50 is 41. All right, now this is why I gave that example in the first part, right? Do you see how, let's see, it would be here. From here on out, what you see here is just what we have here. That's the sequence, the first example that I gave in this video. All right, but let's go through it again. Okay, so this is a new sequence that represents the remainder from this this equation, right? This sequence that we're generating, the nth term equation for the sequence that we're generating. So we have a 2n squared part of it. We took away the 2n squared from the original, and now we're left with 13, 20, 27, 34, 41. So now we're just working as if it was another sequencing problem. So 13 to 20 is plus 7. 20 to 27, plus 7. 27 to 34, plus 7. 34 to 41, plus 7. Okay, and then your formula, un equals a, which is 13, plus n minus 1 times the common difference, which is 7. And I'm going fast because I just did this about 5 minutes ago. You can fast forward, you can rewind if you need to. So it's 13 plus 7n minus 7. It's 7n plus 6. Okay, so what do I circle this? Do you know? I mean, what's the deal then? No, you just tack this on. Check it out. I'm gonna take this. I'm gonna draw an arrow. I'm gonna move my paper in just a sec. And you move it up there. Okay, so you take that answer, and that represents what I have color coded here, right? And so that's a 7, and so you write 7n plus 6. And then what sign do I put there? Well, that 7's a positive 7. If I had a negative here, then I'd put a negative, but it's a positive 7. Okay, and so this right here represents my quadratic equation. It's the formula for the nth term of this quadratic sequence. That's the best way to describe it. Okay, I hope this video was helpful. Have a good day.